What's the difference between ideal and real Ohm's law components? Imagine building a perfect circuit where everything works exactly as planned, with no surprises. That's what ideal components aim for. They follow a simple rule called Ohm's law, which says voltage equals current times resistance. In this perfect world, resistance stays the same no matter what. The resistor acts like a perfect line, with no energy lost except as heat. There are no extra effects or hidden properties. But in real life, things are a little messier. Actual resistors, the components we use in circuits, don't follow this rule perfectly. Their resistance can change slightly because of manufacturing differences. For example, two resistors labeled the same might have tiny differences in their resistance values. Temperature also plays a role. When a resistor heats up, its resistance can go up or down. This is because the atoms inside the material vibrate more at higher temperatures, making it harder for electrons to flow. Physical resistors also have other properties that aren't part of the ideal model. They can have parasitic inductance, which means they behave a little like tiny coils, and parasitic capacitance, acting like small capacitors. These effects become more noticeable at high frequencies. Additionally, if you push a resistor with very high voltage or current, it might get damaged or stop obeying Ohm's law altogether. Engineers choose materials and design resistors carefully to make their behavior as close to ideal as possible. They use high-quality materials with low resistivity and shape the resistors to minimize unwanted effects. But they always keep in mind that real resistors are not perfect. They have tolerances, often around 5%, meaning their actual resistance can be a few percent higher or lower than the marked value. Understanding the difference between ideal and real components helps in designing circuits that work reliably. If you only consider ideal components, your circuit might not perform as expected when you build it with real parts. So, knowing how real resistors behave allows engineers to make better predictions and create more dependable electronic devices. This knowledge is fundamental in circuit theory and electrical engineering, where precision and reliability matter.